Good evening, everybody, and welcome to the virtual home of Princeton Public Library here on Zoom. My name is Janie Herman, and I am the manager of adult programming at the Princeton Public Library. It's my pleasure to host this evening's program featuring photographer Chris Gunn and writer Christopher Wanjek as they discuss their book, Inside the Star Factory, the creation of the James Webb Telescope, NASA's largest and most powerful space observatory. Before we begin, I'd like to extend special thanks to MIT Press for their assistance in arranging this event tonight. If you'd like to purchase a copy of today's books, I will be putting the link into the chat momentarily. The library also has a copy of this beautiful book if you would like to borrow it from us, and I will put that link in the chat as well. This program is being recorded and will be available within a few days on our YouTube channel. So I will now introduce our guests and ask them to turn on their camera to join us on screen. During their conversation, please feel free to ask questions using the Q&A function for our speakers to answer at the conclusion of their conversation. So we have Chris Gunn, who is a photographer based in Washington, D.C. He specializes in creating images of science and technology. His photographs have been featured in Scientific American, Wired, National Geographic, and the New York Times, and he is a contractor with NASA. Christopher Wanjek is the author of Bad Medicine, Food at Work, and the acclaimed Spacefarers, How Humans Will Settle the Moon, Mars, and Beyond. His work has appeared in the Washington Post, Smithsonian, and Live Science. So we've got Chris and Chris here tonight. A little bit confusing, I guess. We'll be able to keep everything straight. So I'm going to let you two take it away for us here. And I know you have some presentations to give, and then we will come back and join in for the Q&A in a moment.
Awesome. Thanks, Janie. I'm going to share my screen. I'm going to share the presentation. So what we're going to do, gang, is we're going to split the presentation. I'm going to describe kind of the science goals and the science element of this mission. And Chris is going to come in and he'll show you describe the highlights of the construction and the people that were involved with it. So thrilled to be here. I grew up in Philadelphia, so shout out to my paisan Larry Ward, maybe to some other Philly people watching. So I'm thrilled to be here. I actually worked at NASA from about 1997 to 2007. That's when I met Chris Gunn. I left NASA. It's a shame. I had this amazing title at NASA. I have to share it with you. I was the senior writer for the structure and evolution of the universe. You got to love NASA when they give you titles like that. But I foolishly left NASA. So I was just thrilled that Chris Gunn got me involved with this project. Before I left in 2007, I was working on Webb a little bit as a writer, describing the mission, but I wasn't involved for all these years that Chris was documenting the construction of it. So I do want to go back to the beginning, farther than the beginning of the project, which does seem like in ancient times. Late 1980s, believe it or not, is when this thing started getting built. I want to go back to the beginning of the universe. And what you're seeing here is actually the deepest image of the universe that we have. This is the Hubble Ultra Deep Field. Maybe you've seen this image. Oh, it's my background for my Zoom. It's how much I love it. So what you're seeing in this image, this is an optical image from the Hubble Space Telescope, and that's going to be key to remember that it's optical. That'll come into play later. But if you what you're seeing, this is actually a really tiny field of view. I mean, if you hold out your thumb at arm's length and look at your thumbnail, it's actually smaller than that, and there's tens of thousands of galaxies in that tiny field of view that Hubble detected. And the deepest ones, if you can look, really squint your eyes in there, you see some of those red dots. They're the deepest, and they're red, and keep that in mind. So I'll give you the punchline here. This is the image. This kind of image is why the James Webb Space Telescope was built. Because the initial goal of the James Webb Space Telescope, Webb as we call it, was to see the first stars and galaxies to turn on in the universe, this evolution of starlight and galaxy formation. And Hubble can't get you there. because Hubble is an optical telescope. And these objects that you see here, the red ones, they're so distant, you might know the concept of red shifting, right? When objects are moving away from us, they are shifted to lower energies. Same as sound, you know, when you're on a highway and an ambulance passes you by and it goes from a high to low frequency, you know, well, that light does the same thing. The universe is expanding. Everything beyond our universe, anything beyond our galaxy is moving away from us. And so that light is so moving so fast and so far away that by the time the object, the light comes back to us, it's been shifted in its energy. So these stars that you see here, they're actually, in the galaxies, they were actually emitting X-ray energy and UV radiation and hot blue light. But by the time it got to us, it has shifted to lower energies. Now, the very first stars and galaxies are actually beyond the realm of our optical range, you know, from red to violet. It's been red shifted out of that entire range to infrared. So regardless of how big Hubble telescope is, it's an optical telescope and will never be able to detect the first stars and galaxies. That's why they created Webb. That's why they made it an infrared telescope. And here's another way to look at it. It's probably my last technical slide, so to speak. This is like the whole evolution of the universe. And so the universe, there was a big bang 13.8 billion years ago. And we actually have detected the afterglow of the Big Bang. It's called the cosmic microwave background. And that light is so distant that that's actually been shifted from, you know, optical and UV and X-ray all the way to like radio and microwave range. But after this Big Bang, the universe actually grew dark again because there was no stars. There was nothing lighting up the universe, and we call this the Dark Ages. And astronomers are trying to figure out when these stars turned on. After hundreds of millions of years, hydrogen gas, which was created in the Big Bang, slowly condensed under the pull of gravity and got hotter and denser, and eventually, through nuclear fusion, ignited into starlight. Now, when did this happen? We don't know. This graph actually was made about 20 years ago, and it's wrong. It's not 400 million years. Already with Webb, after just 2 years in service, we're thinking it's probably 300 million years after the Big Bang, maybe even 200 million years. They're seeing galaxies and stars deeper than we ever can imagine already. It's just rewriting cosmology. But also keep in mind, so we're going to look for when these stars turn on. That's what Webb can do. But Webb can also take a slice of any element of this universe. I'm going to show you how here. It's not a one-trick pony. Its original intent was to see the very early universe, but it's so powerful that it can look at this formation of galaxies over time. And I heard you had this presentation of exoplanets. It can actually study exoplanets as well. It can't find them like some of the things you heard last week, no doubt. But knowing where they are from these other Kepler and some of these other planet finders, Webb can zoom into that and look at those planets and follow the sunlight as it comes past through the atmosphere of those planets and analyze the atmosphere of those planets and determine if there's any biosignatures, signs of life. That would be amazing. But water, carbon, methane, things like that. Could it harbor life even? That's how powerful the Webb is. And also, it's an infrared telescope, as I've been saying over and over again. And so what else can infrared do? Just, how infrared can kind of see through walls on Earth, because infrared energy is essentially heat energy. And with an infrared camera, you can see behind things because that object behind a wall is emitting heat, emitting infrared energy, and you can detect it with an infrared camera. Well, likewise, the Webb can do that as well. Now, this is the famous pillars of creation from the Hubble, this iconic image. This is a stellar nursery in the Eagle Nebula. And you're seeing these great clouds of hydrogen gas just mentioning that, and how eventually the gas condenses into its stars and forms new stars. That's what Hubble sees, and it's beautiful. But Webb can see into those clouds. This is a Webb version, a Webb image of that same Eagle Nebula. And suddenly we're seeing inside those dense, dusty pillars to see baby stars. These are stars that were just formed in the last couple million years. This is the infancy of starlight. And for the first time, really, we're able to monitor that and see how stars are forming in these dusty clouds that we were never able to penetrate before. And Webb does this amazing planetary work as well. This is Jupiter, and it's just really cool. It's Jupiter in a whole new light, so to speak. We've never seen it like this before. And the colors that you're seeing here represent temperature differences on Jupiter. These bands, essentially clouds at different altitudes. The higher up they are, the hotter they are because they're closer to the sun. And that's they can determine the density and the depth of these clouds on Jupiter. This very cool, I thought. So this is a model of the James Webb Space Telescope. We wouldn't just put it on a lawn if it's the real thing. This was around 2006 or so when I was still at NASA Goddard. And what you see here is, we need something really big to detect this really faint starlight from the beginning of the universe. It has to be really big and it has to be really cold because it's, again, infrared radiation, and that's the energy of heat. And you're collecting essentially the heat of these first stars and galaxies. And that's probably not going to be particularly hot by the time it gets to us 13 billion light years away. So this gives you a concept of the scale. That mirror that you see, 18 different segments of that mirror, all the way across, that's 6.5 meters. And then that the sun shield, which I'll explain in a second, that's about the size of a tennis court. And the reason why there's a sun shield is because in space, you don't want the sun to hit the telescope because it will just heat up the telescope, and you have to keep it ultra cold. So essentially, they devised something to block the sunlight because it's not studying the sun, right? They block the sunlight so the sun doesn't hit the detectors on James Webb and keeps them cold, really cold. I mean, there was one instrument on there, MIRI it's called, the mid-infrared instrument. That has to get down to 7 Kelvin, 7 degrees above absolute zero, like 450 minus 450 Fahrenheit. That's how cold this thing can get because of this sun shield and some and that passive cooling down to really cold temperatures. It's just utterly amazing. In fact, Hubble, even if they put an infrared detector on there, it can't really get that cold because it's sitting next to a light bulb called Earth. And Earth is heating it up. But the James Webb is actually 1 million miles beyond Earth. It's 4 times past the moon in an ultra cold region of our solar system. So it's it can get really cold there because of the sun shield and its distant position. The thing is, that's pretty big telescope to launch. And this is everything you need to know about Webb right here. That telescope has to be folded. And that sun shield has to be folded to get into a rocket fairing that's only about 4 meters wide. That's never been done before. Well, here's a quick difference between Hubble and Webb, how much bigger Webb is. And but this is the folding thing I'm telling you about. Okay, so what you're seeing, there was 18 segments. Well, those wings essentially are going to, this is what Chris is going to be showing you. They gotta fold in. And that's not trivial because they have to come back out once this thing is launched and just be perfect. This has to be like one mirror, and you're folding this and then have to unfold it in space. And then the sun shield, that's even tighter. It's like an accordion. And that had to, once in space, that had to open up and stretch out. Again, it's never been done. There was someone I interviewed for this book. He told me, an engineer, he said Webb wasn't constructed, it was invented, because every element of this was just brand new technology. Again, that's what Chris is going to be catching for you. So I'm going to hand it over to Chris. This is the immense job that Chris has covered for more than 10 years. It's your call, Chris. Let me stop sharing.
Chris is trying to get his computer up here. Okay. All right, I was there. There I am. Hi, everyone. Thanks, Chris. That was a great presentation. I actually learned a lot myself. Thank you. All right, so let's see here. Okay. All right, folks, I hope you can see the screen and that it is filling up your screen. I've been a photographer at NASA Goddard for the last 23 years. I spent the very first part of my career at NASA Goddard photographing a lot of award ceremonies and the occasional headshot for someone that needed one. And only once or twice did I actually get a chance to photograph spacecraft. And what happened in, I guess, 2006 is I was asked to join the Hubble Space mission, the last servicing mission to the Hubble Space Telescope. And I jumped at the opportunity to work on that side. The Hubble servicing mission happened in 2009. I think maybe the summer of 2009. And then by the fall of 2009, I was actually looking for a job, and I was asked to join the James Webb Space Telescope program. And then from 09 to 21, every day that I came to work, I had to don one of these clean suits. I had to get all of my equipment cleaned to go into the clean room to document the construction of Webb. I did it at NASA Goddard. I did it at NASA Johnson. I went to Northrop Grumman for some integration there in California. And then I flew to French Guiana in South America to document the launch of Webb. So this is one of the earliest images that I made of the Webb telescope. What you have here is the ISOM structure, which is the structure that all of the instruments, there are 4 instruments that are on the observatory. We have the fine guidance sensor, the mid-infrared camera, mid-infrared instrument, the near-infrared camera, and the near-infrared spectrometer. They all have to fit onto that composite, that skeletal composite structure that you see behind the technician. The technician is about to install a mass simulator onto the structure because this structure went through a variety of tests prior to receiving the actual instruments. So this mass simulator, which actually just simulates the mass of an instrument, was going to be installed on the telescope, onto the structure, and they're going to install 3 more to simulate each one of the instruments. So that's the first really major thing that I photographed on Webb, and I'm still waiting for some excitement. I mean, this was exciting, but I'm still waiting to shoot something incredible. So now, this image here is really special to me because, again, you don't have any flight hardware in this particular photograph. It's an optical simulator for the telescope, but they're running a cryogenic test of this optical simulator in the large cryogenic chamber at NASA Goddard called the Space Environment Simulator, so the SES chamber. So I love this image, and the Office of Communications ran with this image as a web image. I mean, so beautiful. And lo and behold, it was actually picked up back in 2011, maybe, by Popular Science, because it's as if everyone was waiting on a web image. And this was the first thing that actually caught everyone's attention. They talk about the cold chamber because this is the chamber that Webb would eventually be tested in, or at least the instruments will be tested in. And that's what this image is here. This is a test of the instrument package. It's all wrapped in this gold structure here. And this is another image, like I said, before any mirrors, which is what everyone recognizes with Webb. Webb was already getting attention from the media because everyone knew what a big thing was being built at NASA Goddard. This is what work looks like inside of that chamber as they're trying to put it all together. This Ed Shade is an engineer at Goddard, and he is installing thermal blankets. So as Chris mentioned, the telescope operates really, really cold. And to conduct these tests properly, they have to have harnesses and wires, and they need to keep that heat away from the things that need to be cold. So they use these thermal blankets to isolate certain things. So that's what he's doing here. Chris also mentioned the mid-infrared instrument, which is the coldest instrument that's on Webb. So this item here is called basically it's a cover, right, that covers MIRI to help isolate it from the other warmer components on the telescope. And this is a test of that cover. Now here is the completed package of instruments being tested in what's called a gravity sag test. So they have it on a big turnover dolly, and they're basically rotating it to fortunately not hear something drop. Nothing dropped, but this is how they tested for that, the gravity sag test. So now we're on to something kind of exciting here. This is probably one of my favorite photographs made early in the project. This is the container that each one of the 18 mirror segments, as well as the secondary mirror, which is, of course, the 19th mirror on the telescope, were shipped in. So they were shipped in these really fancy containers, purged of all the oxygen, and they made their way through the halls of Goddard. And inside of the giant clean room that we have there, they popped the lid open. This is the actual first mirror that I remember seeing opened. And you could hear a pin drop in the clean room there because everyone was just super excited to see these mirrors. Some people had seen them before, but the majority of us in the clean room had not. You have the mirrors are gold coated, so that gold coating is actually gold because gold reflects the infrared light the best. But the substrate is beryllium, and beryllium is chosen because beryllium is very stable at cold temperatures. It's not going to change shape the colder it gets, and that's really required for the type of precision optical, the precision optical requirements for Webb. So this image is really interesting because it shows how the mirrors were placed onto the flight structure, even though this is not the flight structure. This is a test structure, and that's a test mirror. And they're using a robotic arm. You can see a gentleman under the arm, and you can see another gentleman outside of the arm sort of spotting. And they're using this robotic arm as well as lasers to place this mirror precisely onto the structure. Here's another image of that on the left, and on the right, you see two mirrors have been placed in what's called the Pathfinder structure. Now, the Pathfinder was basically the center section of the telescope that was tested exactly how Webb would be tested eventually down at NASA Johnson. You have two mirrors on that. You have a gold-coated mirror, and you have just a plain beryllium polished mirror. Oops, I skipped one. Really amazing image of the, this is the flight telescope structure, the completed flight telescope structure. You can see the two wings on either side. Everything's open. You have two technicians down in the right-hand corner of this image to kind of give you scale. I mean, it's massive. And this was the first time that I had seen it, and I had a chance to sort of line everything up so that you get the graphic elements of everything. And yeah, okay, I'm gonna move on. Now, This was the very first time that I had seen the mirrors uncovered because they were installed covered, and we had an opportunity to photograph and make videos of this sort of evening lights out test that they were having, and just totally floored by the beauty of this thing and the precision of it as well. On the left, you have an image of another evening test. Now, the difference between this and the previous image, obviously, is that the wings have been folded back. So this is how Webb essentially fits onto a rocket. Those wings are folded back. And all of this is prior to be mated onto the sun shield. But this is the optical telescope structure at night inside of the giant clean room at Goddard. I had an opportunity to make a long exposure, which is why you have the light trails at the top. And the other image is the image of the full mirror after the center curvature test that we had, proving that the optical system was perfect. I'm just going to zoom in here so you can see the details. All the actual light trails are because this is about a two and a half minute exposure, which caught all the movement of the technicians as they were inspecting the mirrors. I really love this photograph because it gives you an idea of what a typical day looked like during a major process during the integration period. So what's happening in this shot is that the observatory, the optical portion of the observatory, is being prepared for vibration testing, which is happening outside of the clean room. So they had to install a clean room onto the telescope. So that clean tent that they're dropping down, it has ladders on the outside and on the inside, so technicians can access it before and after the test. And they're just, there's, I don't know, 30 people in the clean room. There are people spotting the tent. There are people spotting the spotters to make sure that nothing touches anything it's not supposed to. And it's just really love the action in this image. And how I achieved it was by placing lights in the clean room that fired every time I pressed the shutter button. That's why all the clean suits are sort of lit up kind of dramatically, and there's a nice bright light that's hitting the mirrors itself. And it remains one of my favorite images. So from Goddard, the optical portion of the telescope was shipped down to Johnson Space Center in a C-5 Galaxy, C-5 cargo plane operated by the Air Force. It was shipped in a special container and tested inside of this chamber. This is Chamber A, which has history with NASA because the Apollo missions actually used Chamber A to do their manned cryogenic testing, vacuum testing. The chamber itself was large enough to fit Webb, but it didn't go cold enough. So what they had to do was basically fit a helium shroud inside of the chamber. And this is a shot of inside of the chamber while they're doing actual optical work. And as you can see, there's a large opening. And then inside of that large opening, you can see the silver metallic sort of container inside of the chamber. That's the helium shroud, which allowed Chamber A to get cold enough to test Webb. This is a photograph from inside of the chamber looking out as they're preparing to push Webb in. And these are photographs from the actual installation of Webb into Chamber A. Get an idea of scale. You get an idea of clearances. That image on the right was actually made, not for the beauty, but to make sure that it fit. They put me up on a man lift to check those clearances from the secondary mirror support structure to the top of the chamber. Of course they had measured it before, but you always want to make sure. And this is an amazing image of the inside of the chamber with Webb inside the chamber. And just, I'm going to technically tell you how I made this image. Obviously, I was on a lift. I was about 8 stories up, and in a man lift with the driver, and I was remotely controlling a light source that illuminated the back wall of the chamber. Now, these walls were flat black paint, but I still had to pump enough light onto it so that I could create a reflection in the mirror. If I hadn't lit that back wall, then we wouldn't be able to see the mirror in this image. And I was able to pull it off, no pressure, or there was actually a lot of pressure to make this happen. And I'm really pleased with the results. This is an image of the observatory post-test. So they just pushed it out, and we got this lovely image of it. So from Johnson, by the way, the Johnson test was a 90-day test. It was a hurricane during the test. Telescope survived the hurricane. Johnson Space Center survived the hurricane. There were lots of obstacles during the entire integration of Webb, but we seemed to manage to get past all of them. But after it left Johnson, it arrived at Northrop Grumman, again by C5 Galaxy, and this is a photograph inside of Northrop Grumman's clean room. Basically, you're still looking at the optical portion of the telescope. There's no sun shield here. That's on the other side of the room, and they're working on that, the sun shield and the spacecraft bus. And on the optical part of the telescope, they're just modifying things, making sure everything is perfect. What they're doing here is doing an inspection of the frill. The frill is the sort of black material that surrounds the mirror, the 6.5 meter mirror. And the frill is designed to control stray light. But they want to make sure the frill is actually kind of a rigid blanket, dark blanketing material. They're trying to make sure that it's going to work perfectly when the mirror is open, that it lines up perfectly, and they have to do these regular inspections and also do some modifications to the blanket. Now, I included this image because I just want to show you a really cool time-lapse video that I made. So my first role as a photographer on a project is to capture things for engineering purposes. If I get pretty pictures, that's a bonus. So the purpose of this shot, of positioning this camera up on a crane, was to capture the secondary mirror support structure as it's being deployed. This was a 12-hour day, and through the magic of cinema, we've sped this up. But during this 12-hour day, the secondary mirror support structure was actually deployed under its own power. And you see now. It took all those people in 12 hours to make that happen. And at the end of that, this is the shot. This is also the shot that we use for the cover of the book. But basically, this sort of explains the light path of the optical observatory. So the light hits the primary mirror. Now you can only see the center section of the primary mirror in this photograph because the two wings are folded back. And then that light bounces off the secondary mirror, which you can't see the front of it. You only see the back of that mirror here, which is covered in black Kapton tape. But you can see the front of the mirror reflected in the primary. And then you can see the primary mirror reflected back inside of the secondary. But that light from the secondary mirror then goes through the center section. So you see the black shape. It looks like a mirror, but that's actually the aft optics assembly. And inside of the aft optics assembly, there's another mirror. There's a tertiary mirror. And then that feeds the light to the instruments inside of the ISM structure that I showed you in the second slide. Hope you understand that. Now, this is what the integrated telescope looked like, all folded up. So the sun shield, you have part of the sun shield on the back, part of the sun shield on the front. And this is just, prior to it being closed up completely, as you saw in one of the photographs that Chris showed you. And this is one of, I think, 2 times that the actual sun shield was fully deployed, fully tensioned, and we had an evening with it to make some photographs, and absolutely amazing. And this image here was the last time that I got to photograph the telescope with the mirrors fully deployed. Now, they never deployed the mirrors and the sun shield at the same time on Earth, but this was the last time that the entire mirror was deployed. And we made this photograph just prior to the telescope being put into a shipping container to be sent to French Guiana for launch. All buttoned up. The silver section, sort of square section at the bottom, that's a spacecraft bus. So that is where all the flight electronics are. That connects to the tanks for propulsion. That's the sort of the business end. And of course, the optical portion is on top, and the 2 sort of purple sides, that's the sun shield, all folded up. And this is how it fits into a rocket. And here we are. This is French Guiana. This is the day that the image on the left there is the day that the rocket was going to roll out to the launch pad. And the image on the right there is from my remote camera, which was too close for me to operate by hand. So we had a trigger on this camera that actually fired when it heard the launch. So as the launch started, we had it set so that, you know, it would start making photographs as soon as it heard the sound of the launch. That's how the remote worked. And that's my presentation, folks. Hope you enjoyed it.
Wow, that's just so interesting. Thank you both. What a remarkable achievement to tell us not just the whole project, but the documentation that went into this creation and the creating of this book. So I'm really going to encourage anybody who's with us on this call at this time to put your questions in the chat. And, you know, so I'll get things started. So what was your working process like then in creating the book? So obviously, Chris Gunn, you had the photographs. And then how did the other Chris interject with the text, or how did that all work?
Well, I'll take this, Chris. I'll tell you, I almost approached this the wrong way, because I mentioned I was the senior writer of The Structure and Evolution of the Universe. So at NASA, I was so geared towards cosmology and the scientists and the astrophysicists and the theorists and all that jazz. But when I saw Chris's, and that's when I wrote the book, the first person I went to was John Mather, the guy who won a Nobel Prize and was involved with this project. But when I saw Chris's images, I realized it was all about the workers, the engineering, and the dedication. And that changed my tone radically. I never understood the job the way until I saw those images. And so I went back and forth. Chris was feeding me images, and I was just blown away. But my mission, of course, was to describe up front of the book the science and the history of it.
That's awesome. We do have a question here. Somebody wants to know, and I'm not sure if either one of you knows the answer to this one. Maybe it's more of a science one. What happens if the telescope is hit with a particle in space?
Ooh, and it has.
Well, yeah,
Go ahead,
I
Chris.
mean that has happened, and it was expected. I mean, that's one of the reasons, for example, as to why there are 5 layers of the sun shield to protect it from micrometeorite strikes. And they anticipate that it will happen again, but they have determined that it doesn't happen frequently, that it gets hit with a large enough micrometeorite that it will affect the performance of the telescope. So
Okay. And then another question coming in from Robert wants to know what went wrong, if anything, with getting the telescope to its current position. Were there problems, or was it a relatively smooth?
No, the exact opposite. And ESA doesn't get enough credit. So that rocket that Chris showed, that's from the European Space Agency. And that launch was so perfect. It was at such the right trajectory that it put it in the orbit, and NASA didn't have to expend any gas or fuel, to maneuver it just a little bit to get it into its final orbit. And because of that, because they were able to save all that fuel because of this perfect launch, the mission lifespan has been extended by 15 years. This was, maybe a 5-year mission, maybe up to 10, but now it can go up to 20 years because it has enough fuel to do its minor maneuvering, because it didn't have to waste it in the getting it perfectly into orbit.
Interesting. So someone else wants to know, was there ever a moment when it looked like the Webb telescope was close to failure and might not happen? And if so, how did the team get past that?
Go ahead, Chris.
close to failure, no. I would say I never saw anything close to failure. Were there challenges? Sure, but that's one of the things that impressed me so much about the team that was put together from different contractors and NASA employees and what have you. There was nothing, and I mean nothing, that I ever saw happen that wasn't fixed or wasn't figured out. And I guess that's something that I've noticed in all of NASA, and that's why I think it's one of the best places to work, is because these are problem solvers, so nothing stops them, So
Right.
never saw anything catastrophic.
It was congressional funding it wasn't on an engineering side, it wasn't on the talent side. It was whether Congress was going to continue providing the funding for it.
Right. And so someone else wants to know, how much fuel did the telescope carry to maintain its position at L2? And how many feet thick is the sun shield? Are these getting too technical? Or
Well, I don't know how much fuel it carries. The sun shield is something that we should know. There's 5 layers.
Well, the layers are very thin.
Yeah, it's like tissue paper. I mean,
it's a blanket material. It's like Mylar, right? And it's very thin. And one of the interesting things of the design is it's sort of stitched together in a patchwork, so that if there is damage to one, it won't like rip the whole sun shield. So the sun shield, would stop at that section, right? That's part of the design. And there are 5 layers, again, that redundancy. But also, because of the 5 layers, it's a thermal thing, so that, there's heat actually trapped in between the 2 layers, or in between 2 layers. So it's another engineering marvel. And when you see the whole thing tensioned in real life, it was pretty amazing.
Then I think the first layer is doped with silicon, and that's why I gave it its pinkish hue.
Actually, I'm not sure what's giving it the hue. That could be. I do know that it's different than the other layer. So the underside is different than the other one.
Yeah, it's doped with something.
Gotcha. And in terms of how much fuel, I don't know how much, but I do know that because of the extraordinary insertion into orbit, they have more than enough fuel for the designed mission life. In fact, the mission, they've thrown out some extraordinary numbers in terms of how long the mission could be extended, because they didn't have to use extra fuel to get into that great orbit. So.
Okay, and we have a question here. This is definitely for Chris Gunn. Can you discuss the photo gear used? what cameras and lenses. So someone here like really interested in the fine detail of the.
That's awesome. I like that. Sure. So I started off, I mean, I used several different cameras throughout the process of documenting Webb. It was, a good 12 years for me. Nikon digital cameras, full frame. I use the D3S, the D3X, and the D4S, if you know what those are. But they're the heavy duty flagship cameras that can take a beating and have an actuation life. Their shutters last 200 and 300,000 shutter clicks. But somewhere in the middle of the project, I realized that I had a problem, and that was that everything about Webb is perfect, geometrically perfect. There's a lot of symmetry there, and if you point a wide angle lens at something that's symmetrical and you sort of look up at it, it distorts. I mean, everybody sees buildings that sort of bend backwards and that sort of thing. And distortion ruined images of Webb that I would make with a wide angle lens on a 35 millimeter based camera. So eventually I went to the medium format Hasselblad camera, which the project manager, Bill Oakes, agreed to actually get for me. And the medium format Hasselblad actually changed the way I photographed and changed the quality of the imagery that I made for the project. It also slowed me down. It's a slower way to shoot with that camera, so that I often say I make photographs, but you actually are making photographs when you're using a camera that slows you down. You're looking at things more intricately. You're figuring out how to light it and where to best position the camera to reduce distortion and to really make images where the subject, in this case Webb, would just kind of jump off the page and would make people feel like they're inside of the clean room. So that was my goal, and that I achieved it with those cameras.
Okay. So this is a question for me. So last week at the library in our community room, we actually had Joshua Wynn there, who is the author of a book called The Little Book of Exoplanets. And he was talking a lot about exoplanets, and he's part of the Transiting Exoplanet Survey, which currently has a satellite. And he's been very involved in that. And he was telling us that NASA is building a new telescope that will launch in the 2040s that will image these Earth-like exoplanets and maybe finally discover where advanced life exists elsewhere. So, because the Webb telescope wasn't conceived specifically to study exoplanets, but has already begun delivering some spectacles about it, some readings about it. So are you going to be involved with that project, either of you, documenting it in the same fashion? Or have you been asked? Are you aware of this? Are you aware?
I am.
It was like, oh, we had to stay alive until 2040 so we can discover if there's life on these exoplanets.
So I'm actually working on the Roman Space Telescope right now.
Okay.
Which sort of is the telescope in between Webb and the Habitable Worlds Observatory, which is the observatory that you're talking about.
That's what it's called. Okay. Oh yeah, Larry put that in, the Habitable Worlds Observatory. Thank you.
Yes, yeah, mouthful. So obviously, if I'm still around, I would love to photograph any part of the Habitable Worlds Observatory. But Roman's also pretty amazing. Now, Roman isn't necessarily looking for exoplanets, but it will answer some questions about dark energy and dark matter, because it's a wide field. The original name was the WFIRST, or Wide Field Infrared Telescope. So it has such a wide field that will enable us to see sort of the dynamics of the universe that you don't see with Webb or with Hubble, right? It has, instead of 18 mirrors, it has 18 sensors, right? So if you can imagine, this being the sensor of your camera, well, now there are 18 of them stuck together. So it's a huge sensor, and it'll show how, galaxies collide, sort of, and how they affect the other elements of the universe around that. So we're hoping to find dark energy, or some of the secrets of dark energy and dark matter. Now, I have spoken to a couple of folks that worked on Webb, and anytime I say anything about Roman, they always mention habitable world. So work has started in earnest on that planet finder. So I'm excited about it.
Yeah, there was a lot of excitement in the room last week about the exoplanets, and the little book of exoplanets was a hot seller last week. So I think we're in for some interesting times ahead. And so we have here another, well, it's kind of both a comment and a question. Eileen says, thank you both for a great presentation. It says, Chris Gunn, you were there for all of the milestone events. So what is a special memory for you that was just a jaw-dropping moment or extremely powerful moment, and that's something that you will remember forever?
Hi, Eileen, first. I know Eileen. Jaw-dropping was launch. And, this was only the second launch that I had ever photographed during my career at NASA. And launches are pretty special. And, all the photographers want to shoot launches. So I had my 3 cameras, and Bill Ingalls from NASA headquarters flew down to French Guiana to also document the launch. And I said, hey, Bill, you're the launch master. I just need, a couple tips. And I think he only gave me 2 tips. But we were able to set these cameras up in a way to capture the launch. And when I went to retrieve that one camera that was sort of on that river, this is the momentous occasion, there were 2 other photographers there from the European Space Agency, and we raced to our cameras to get them, to retrieve them, as if we were competing with each other. And then we raced back to the cars with our cameras, and I raced back to the car, and I turned that camera on, and I started scrolling through photographs, and I saw that photograph of the rocket lifting off with the plume and reflected in the water. And I'm pretty sure I cried, just because I had no idea whether or not the remote camera was even going to work. And so to be able to capture the image that I made, it shows the rocket successfully launching, and to just show where we were. I mean, like literally in the jungle in French Guiana. It was just awesome to see that image. And other than that, I mean, almost every day working with the team was great. I mean, it's just a really great team of people to work with, the family. So.
Okay, so I mean, this has been such a fascinating conversation. I think we could probably sit here and talk all night, given the interest of everybody here online. But we're coming up to the close of our hour, so I'm going to let Barbara Webb's question that just came in here. Barbara Webb is, of course, the daughter-in-law of James Webb, and we're so glad to have you online with us here, Barbara. I'm not sure if your husband is there with you or not as well. I know you're logged on under you, but she wants to ask this. Is it an overstatement to say that the Webb is one of the most audacious engineering feats in human history?
Not an overstatement whatsoever. Chris, your take? I mean, I quickly mentioned that, this, as I said, an engineer said this thing was invented, not built. I mean, the scale of it, I don't know how you compare it to the Panama Canal or something like that, but the technical scale, the number of people, hundreds of millions of human hours going into it, immense team. Chris can probably say more, but it just for as far as NASA is concerned, I think it's its most complicated instrument ever built and launched successfully.
Yeah, and in terms of scale, I mean, it has been compared to the Apollo missions. Of course, this was not manned, So yeah, I mean, I do think that it was audacious, and probably one of the most audacious engineering feats, because you're tossing this thing into space and you're expecting everything to work perfectly. All of the deployments have to go flawlessly. If one thing didn't work right, then we had an issue that was going to not necessarily be catastrophic, but then take, tons of manpower to figure out how to rectify a million miles out or somewhere along that path to a million miles. So yeah, I mean, I I wonder how some of these guys slept at night knowing how complex this was, how complex the observatory is and was to put together.
Yeah.
I brought it up.
Well, thank you both so much. So listen, this is a beautiful book. It's got all these wonderful photographs and the writing and the story. It's it's a coffee table type of book. I think it'd make a wonderful holiday gift. I put the links in the chat if you're interested in purchasing, all the places that you can get it. If you live locally, our library has a copy. I'm sure many other libraries have a copy as well. It's that kind of book that definitely belongs in libraries and in homes everywhere. And I want to thank Chris and Chris for taking the time to be with us here tonight, to show us the images, talk about their experiences with this wonderful engineering feat. And I think people think, oh, I'm going to be a photographer, and never realize that you're going to also have to learn so much about space exploration and or be a science writer, and how all these things can happen and come together. And it's just been so fascinating and interesting. So I think that's going to wrap us up here for tonight. So this will be up on our YouTube channel, YouTube/Princeton PL, within a couple of days. And thank you again, Chris and Chris. And
Thank you.
And if you get involved with the Habitable Worlds, we'll be looking for some photos from that as well. We hope that you'll get to photograph it, and
Awesome. Thank
or
you.
maybe help discover us an exoplanet or two. So
Okay. Well,
okay.
Webb might as well.
Yeah.
Thank you for the
That's right.
opportunity, Jen.
Thank
Webb
you so
might
much.
find us an exoplanet. Okay. Thank you, everybody. Good night.